Hello everyone, my name is Ray, who is in charge of the technical service of IDC, the Industrial Device Connectivity. Today, I'm going to introduce you one of the industrial protocol, the EtherNetIP. Before proceeding with this course, we recommend you get familiar with serial and Ethernet essentials that will help you understand some basic knowledge. And this module is intended for all technical service engineers. In this course, you will learn the EtherNetIP essential knowledge, which helps you to configure Mozart IEG products. After this course, you will have knowledge of the history and the network topology of EtherNetIP, and also how the EtherNetIP devices communicate to each other. Let's start today's course. Before learning EtherNetIP, there are some background information I would like to introduce. The first thing is an organization, Open DeviceNet Vendors Association, or ODVA. The ODVA is an international organization that supports computing network technologies based upon the Common Industrial Protocol, the SIP. These include DeviceNet, EtherNetIP, SIP Safety, and SIP Sync. Members of ODVA include representatives of leading automation companies, for example, the Rockwell Automation. And if you want to know more about ODVA, you may visit them on website www.odva.org. The second thing is the three levels in most automation architectures. First, we have an information level in which supervisory control and data acquisition, or SCADA stations, monitor the status of variables in the controllers. Also on this level, we will expect to find PLC, programming terminals. At the control level, we will expect to find time-critical complex high data volume devices like I/O racks, high-performance variable speed drives, and plant-level man-machine interfaces. At the device level, we will expect to find simple, low-cost, and low-data volume components, like distributed I/O blocks, motor starters, and simple HMIs. In a traditional architecture, the PCs talk to the PLCs. The PLCs talk to the I/O devices, whether they are simple or complex. The only route for information from the device and the control levels to the information level is through application code in the PLCs. The three-tier structure is popular description in industrial field. Let's start to learn the EtherNetIP. Today, I will introduce the essentials for EtherNetIP. This includes the role of EtherNetIP scanner and adapter, and how they can communicate to each other. This is the agenda. I will introduce the EtherNetIP network topology first. Then, how the EtherNetIP scanner retrieves the EtherNetIP adapter information and locates the adapter on the EtherNetIP network. The last part is how the scanner and adapter exchange the data or information. Please take a look at this topology. This is a water and wastewater monitoring system. Generally speaking, there should be a master that sends requests to a slave, and the slave will respond to provide some information to the master. In EtherNetIP, the character of master is called EtherNetIP scanner. In this case, the SCADA, who is collecting data via the EtherNetIP network, and the slave, the meter, that is monitoring the water information, is called EtherNetIP adapter. There can be many different kinds of the meters or devices on networks or EtherNetIP adapters. How can the scanner be aware of each of them? The EtherNetIP scanner recognizes the adapters through the electronic data sheets, the EDS file. To get the information of each EtherNetIP adapter, the EDS file records all the information that the scanner should know about the adapter, the vendor information, the functions it supports, and how to communicate with this device. In this slide, it shows the installation tool of a Rockwell EtherNetIP scanner device, which helps the user to import the EDS file of an EtherNetIP adapter and also the EDS file of our Mozart MGate 5105. When the scanner imports the EDS file, could it find the adapter? Not really. It still needs to send out the request on the network, then check the response to find the specified adapter. There are two objects it will check. The first is the basic information of the adapter, which is recorded in the identity object with the class code 01. The class code is a hexadecimal value unique to an object. Use the class code to identify the object class when accessing objects in devices. The identity object provides the general information about the device, includes the vendor ID, device type, and the product code. The second one is the TCP/IP interface object with class code F5. The TCP/IP interface object provides the mechanism to configure a device's TCP/IP network interface. In the slide is an example to use the simulator EIP scan to get related information from an EtherNetIP adapter, which is IP is 192.168.35.117. In general, the scanner will read or write from the assembly object from the adapter. The assembly object binds attributes of multiple objects, which allows data to or from each object to be sent or received over a single connection. Assembly object can be used to bind input data or output data. The terms input and output are defined from the network's point of view. An input will produce data on the network, and an output will consume data from the network. And also, the EtherNetIP defines the originator to be the EtherNetIP connection establisher, and the target to be the device which accepts the connection request. So, if the data comes from the target to originator T2O, also called input, the other way, O to T, called output. When configuring EtherNetIP devices, there are some parameters users should know. Here is an example when using EIP scan, which is a popular EtherNetIP scanner simulator. The first one is connection point. As I mentioned before, in most cases, the EtherNetIP scanner read or write from the same object, the assembly object. But what part of the assembly object? The address or attributes could be very different for devices from different vendors. For example, our MGate 5105 is at 100 for output O to T, 110 for input T2O. User can find this information in the user menu of the device. The second thing is the data size. In most devices, this is a fixed size for the device, but not when using a gateway. A gateway may be flexible for the data size because there are so many different kinds of devices could be connected to it. The next thing is the packet rate, which also called requested packet interval, the RPI. It defines the frequency that the EtherNetIP scanner should get updates from the adapter. If the data is not updated within the interval, it will report as a timeout error. The last thing is the connection type. There are two types, point-to-point or multicast. Let me explain it in the next slide. Just like the name says, the point-to-point is only between one EtherNetIP scanner and one adapter. When the adapter has data should update to the scanner, it will directly send the data to it. It won't wait for a request. If it's multicast, user should configure the EtherNetIP scanner and adapter separately and start them by the configuration tool. Then the adapter will start to send the data out to the EtherNetIP network by multicast packets. All the related scanners on the network will receive the data and handle it. And that's all. To configure an EtherNetIP scanner or adapter, you only need to know above information. And there are 3 key points. The devices on an EtherNetIP network are EtherNetIP scanners and adapters. The scanner is who consumes the data, and the adapter produces data. For each adapter, it should have an EDS file for the scanner to import to recognize the device. When configuring, there are 3 things you may have to do: the connection point, connection rate, and the connection type. Thank you for your time, and don't forget to take the quiz to see how much you have learned from the course. Hello everyone, my name is Ray, who is in charge of the